Low-level programming languages. A low-level programming language is a programming language that does not provide any or much pensiveness from a computer's instruction set architecture. Such programming languages are easily interpreted by the computer rather than by a human, and thereby impose complexities in terms of understanding and using low-level programming languages upon the programmer. The world of software technology has seen the advancement of two types of low-level programming languages: machine code and assembly languages. The lowest level language that is used to program computer viruses is assembly language. Machine codes are not used to program viruses, especially because of their distant relationship with humans in terms of understandability and usability. It is logically possible to create a virus program using machine code, but realistically it is impractical because of the amount of distress a programmer endures to write a small piece of faintly destructive code. Furthermore, since machine codes are largely dependent on the hardware architecture, it limits the portability of the virus. Machine code thereby proves to be very disadvantageous to a virus programmer, which explains the reason it is not used to program viruses. Hence, we will focus on assembly languages and programming viruses using assembly languages. Developed in the early 1950s, it was then considered as one of the most efficient languages because it eliminated most of the error-proneness and time consumption of machine code, and was considerably easier to code with and more understandable compared to machine code. Most operating systems back then were coded using assembly language owing to its imminence to the machine. Its imminence to the machine can be illustrated by the fact that in a typical program written in assembly language, a single line of assembly code corresponds to a line of machine code that can be loaded into memory and thus executed. A program written in assembly language is converted to machine code with the assistance of an assembler. The complexities of modern computers make coding applications using assembly language very complicated. However, the use of assembly languages is not extinct from society today. Most embedded systems, compilers, device drivers, and real-time systems are coded using assembly language. Assembly languages provide the implementation instructions for a particular CPU architecture. Thereby, they are dependent on the CPU architecture it was written on. This reduces the potential for the portability of programs written using assembly languages across different computer instruction set architectures. Assembly codes comprise of mnemonic opcodes. Those are operational codes specified in small English-like words, which provide for better understanding and easier usage. The use of such symbolic references is one of the key features of assembly languages. These opcodes are of two distinct types: executables, those are machine opcodes, and assembler directives, which are non-executable and dependent on the assembler, also known as pseudo-opcodes. Assembly language programs are generally faster than programs created in high-level programming languages. This too is reasoned by its imminence to the machine and the fact that it does not need any sort of compilation or interpretation. It simply needs to be assembled. Assembly languages are acknowledged as very powerful because of the unlimited power a programmer has over the machine and the facility of implementation without any restrictions. Assembly language programs are very small in size, which provides well for situations where space is an issue. Assembly language designs are structured in a very simple manner. Each instruction typically consists of an opcode and 0 or more operands. Assembly languages are also designed to permit pseudo-opcodes, which provide directives to the assembler to be followed at assembly time. There is support in assembly languages for certain control flow statements akin to go to and if then else too. Assembly languages are designed to provide the programmer with the facility to create procedures and functions that aid in programming. This allows the user to factor out recurring details and group together statements that correspond to a particular activity. The syntax of assembly languages follows conventions explained by the following extended Backus-Naur form syntactical rules. A label is a symbol name, and an instruction is either an encoded pseudo-op, synthetic instruction, or an instruction. As other programming languages do, assembly languages have clearly defined lexical features. They are concerned with case distinction, comments, labels, numbers, strings, symbol names, special symbols, and operators and expressions. There is an immense amount of virus programming conducted using assembly languages due to the intensity of harm such a virus could cause and the less complicated implementation of such a virus. Creative viruses can be coded using assembly languages due to its features of directly handling CPU registers and memory locations in the code itself. The ability to jump from one host program to another has been identified as a much less complicated process in assembly languages, unlike in high-level languages where people have yet to attempt such programming acrobatics. Assembly language gives a virus programmer the complete control of the system's resources and allows the programmer to use them the way she or he wants to, rather than the way another person thinks she or he should. In the case of high-level languages, the compiler is what determines the resources and their usage. The lexical features of assembly languages prove the simplicity of the language structure, which also aids programmers to code viruses using assembly languages. Programs written in assembly languages are rather small in size, and therefore provide a great deal for the spread of viruses across similar computer system architectures.